and our speakers are Kevin Murrell, Roger Johnson and Delwyn Holroyd. Kevin is trustee and co-founder of the National Museum of Computing, TNMOC, and our meeting secretary and project leader of the HEC-1 project. Roger is our secretary, and Delwyn is chair of the TNMOC Volunteer Committee and our CCS project leader of the Harwell Decathlon Computer, ICL 22966 and ICL 1900 projects, amongst lots of other things. The speakers are going to describe how one of the world's oldest surviving computers came into being, its legacy to the industry, and its preservation and display at TNMOC.
Well, good afternoon, everybody. A slight elaboration first. The picture that you can see in front of you is not the HEC computer. As you'll see shortly, we've been interested to try and find out which machines were on display at the old Birmingham Museum of Science and Industry. And I've got a variety of people sending me pictures. And apparently this is part of a machine that was on display at the old Science and Industry Museum. And I'll have a quick word with Dick, and he might find some space in Resurrection to publish it, but we just thought there's an off chance if anybody actually recognises what it is. Now, we were advised it was in the computer section. There's some big pentode looking things in the middle there, 8 of them. It's all pretty regular. Whether it's part of a tab or a punch, I'm not sure. Now, I can't see any waving frantically from the back. So, no offers? No. Alan, go on.
No, I'll say something to you separately. It could well be an electronic calculator of the period as used on 555s or something like that.
So that would be a powers machine?
A bit, yeah. It depends. Anyway.
Oh, right, okay.
Let's talk afterwards, because the valves used would give a hint.
Right, thank you. Right, thank you for that diversion. I understand. Yes, we'd like to tell you about the HEC-1 computer, which, can you actually hear me now? I hope it's yeah. Okay. Which has recently arrived at the National Museum of Computing. Now, I have a relatively easy job here. As an amateur at everything, I'm an amateur historian, so Roger's doing the real history bit later on. I'm an amateur engineer, so Delwyn's doing the real engineering bit later on. But if I've got anything, I've got a knack of wheedling machines out of museum stores and bringing them to the National Museum of Computing. Basically, I will sign anything. But that's been quite successful. It hasn't been successful with the Science Museum yet, but over time. What I want to talk about is, in my short section, is rescuing the HEC-1 machine, discovering it's still intact, and finding the machine, and then bringing it back to the museum. And I thought I'd go through the sightings of when we'd seen the HEC computer. And in fact, it dates back to Martin Calmer-Kelly's book, ICL, Business and Technical History. And it really is just when Martin's discussing the HEC computer, the BTM in general, there's a footnote to say that the HEC-1 computer is on display at Birmingham Museum of Science and Industry, which must have been during the 80s, and perhaps just about into the early 90s. Now that led to the second sighting, and that's a visit by Birkbeck, Roger Johnson and colleagues from Birkbeck College, to go and see the HEC-1 computer, and you'll realise the link with Birkbeck shortly, with a view potentially of having the machine on display at Birkbeck. It didn't quite happen. There were problems in actually arranging the loan agreement between the museum in Birmingham and a non-museum as Birkbeck. But it did actually on Rogers and Birkbeck's, I was going to say command, but request, Chris Burton, who many of you know obviously from Manchester Bay and the CCS, went to the storage centre where the HEC-1 was being stored at the time and made a very complete survey of the machine, detailed photographs and a detailed report on the condition the machine was in. Now that's actually been invaluable because it did pin down all of the elements of the machine at the time, including a couple of extra drums as well, which we're still looking for. We then have 4 years where actually nothing happened. But during that time, I've been looking at Chris Burton's pictures from the museum store and seen in the corner of one of the pictures the control panel for the Harwell Decatron computer, which is a machine I'd recognised. So we went back as a CCS back to the storage centre in Birmingham in 2008, and the HEC-1 was strapped together in a pretty awful sort of packing case. We managed to take the HEC-1 apart out of the case and arrange it into order. But I must say my attention was mostly on the Harwell machine, and it's the Harwell machine that we actually concentrated our efforts on. We went back in 2010 to take Dr. Raymond Bird, Dickie Bird, back to the collection centre, the British Library, to actually video in front of the machine. And for each of those years, Roger Johnson and I have gone out for a Christmas lunch with Dickie Bird every year. And every year Dickie said, when are we going to get the HEC-1 out of Birmingham? And it got more and more difficult. And so we actually really must do this now. And we started negotiations with Birmingham in 2014. I'm happy to say that actually went quite well. One of the useful things is we had a good track record with Birmingham over the Harwell machine, so they were fairly generous about the terms of letting us have the HEC-1 machine. And in 2015, it was late last year, transported to the museum. Rachel mentioned it's one of the very earliest intact machines still around. So it's quite interesting about how it actually stayed intact. Now, construction completed in Letchworth in 1951. The teams then, and this isn't that, we're not actually sure of all of this yet, the team then moved on to updated versions of the HEC-2 and a marketable machine, and a machine that was actually exhibited. HEC-1 stayed at Letchworth and somehow stayed intact. Now, we suspect certain parts were borrowed because, as you'll see from Delwyn's report later on, quite a lot of the valve positions were pretty random by the time it came to us. But the machine stayed largely intact. We have some reports of a proto-museum being set up at Letchworth, and the name associated with that is Bertie Bellringer, which is certainly a name to conjure with, isn't it? That collection was subsequently moved to Stevenage, and unfortunately the building it was in wasn't really suitable, started to fall in, Peter Bonfield in charge, there wasn't funds to actually do anything else with them. And the artefacts were then dispersed and offered to museums around the country. Now, how it came into Birmingham is quite odd. It was labelled as the Apex machine, which is one of the machines designed by Andrew Booth at college. But the machine was actually made in Fenny Compton, which isn't that far away from Coventry, which is Fenny Stratford, sorry.
No, it is Fenny Compton.
It is Fenny Compton. Fenny Stratford, it's not a fear, it's Fenny Compton. And that's quite near Birmingham, isn't it? So it was decided, in fact, actually, it should be offered to the Birmingham Museum's Trust for display, which is, I mean, just balmy, but it was sent to Birmingham. It was on display at what was a wonderful Museum of Science and Industry in Birmingham for many years. When that closed, it was moved to a pretty poor storage facility in Charlotte Street in Birmingham city centre. But we believe the machine was separated into 4 constituents before it was moved to Birmingham. And if nothing else, Birmingham, while they didn't have it on display, at least kept all the items together. By the time we went back to the storage centre in 2008, the storage centre had moved to a new purpose-built facility just outside the city centre, which is really quite state-of-the-art museum storage centre. And the final part of the journey now was 2015, as I say, last October, I'm going to say, or November. October was actually, we completed the agreements with Birmingham and moved to the National Museum of Computing. Birmingham, it's very difficult for a museum to gift an item from one to another museum. So typically it's done as an inter-museum loan. And typically they run for 3 years and get restored and renewed every 3 years. Typically what happens, we have a lot of equipment on loan from the museums of Liverpool. And they gave us a 3-year loan for that, with the proviso, I was told with a big wink, you must never bring it back. So we basically have the machine for in perpetuity. One of the interesting things when the machine came to the museum is a representative from Birmingham came down with the machine to check it had arrived intact. I'm feeding back here on something else. He was particularly interested in why we thought, what was the machine, what defined the machine as a candidate for restoration, and what defined the machine as a candidate for simply conservation. He came to see as well the Harlow machine, which was working in absolute glory, surrounded by school children, so it was an absolutely perfect example. But that's one of the things that we will touch on, I suspect, later on today. We have, I'm going to hand over to Roger Johnson in a minute, and then on to Delwyn. And we have 3 short videos of the machine when it was on display at the Business Efficiency Exhibition in 1953 at Olympia. We might have to stop the recording of this because these videos have Getty Images written all over them. So we might have to think about that. We might have to take legal advice on that. But Roger, can I just carry on?
Right. I'm going to talk about the history of the HEC as we know it. I'm going to go fairly rapidly over parts of the story that relate to Birkbeck because a number of you will have heard me talk about Andrew Booth's work relatively recently. So let's just start by just reminding ourselves about BTM. BTM originated as an offshoot of IBM. The Tabulating Machine Company was founded in 1896 in the United States, and it grew by a process of mergers to become IBM in 1917. In the process of moving from being the Tabulating Machine Company to IBM, it founded a UK subsidiary called the Tabulator Limited, which sold the products, the punch card products in the UK, and later acquired the rights to sell them throughout the British Empire. And that machine was renamed the British Tabulating Machine Company Limited in 1907, BTM as we know it. Initially it sold IBM equipment, and then it later on used IBM patents to build BTM products distinct from IBM ones. And the critical thing was sterling currency. And sterling, of course, was used throughout almost the whole of what was then the British Empire, not in Canada. And the agreement, the royalty agreements, were that BTM had sole rights to sell IBM equipment equipment and equipment developed using IBM patents throughout the British Empire outside North America. That went on for quite a number of years and was successful. There were difficulties over the royalties, and in 1949 BTM and IBM decided to go their own way. Martin Campbell Kelly, in his book on ICL, describes it as a strange decision, and I agree with that, and I acknowledge it's a strange decision as being, I think, Martin's phrase. Just at the very point when there is going to be what I suppose today we would call disruptive technology in the form of an electronic computer, and with IBM, with its substantial resources, developing a machine, BTM decides to go its own way. On the other hand, I think I was realised really in the last few weeks, and I was talking about this with some of you before this meeting, I think one has to remember in 1949 that if you were on the board of BTM, you were selling punch card equipment throughout the whole of the UK and the British Empire. It was a huge spread, and your only real competitors were Power Samus, and they were, I'm sure, regarded as being not quite in the same class as BTM. So apart, therefore, from Powers, BTM had this vast market, and therefore I think a substantial measure of self-confidence. But looking back, it seems a strange moment to choose to detach themselves from BTM. Anyway, the board of BTM decided that for the long term they would need to engage with computer technology, but their decision in 1949, and again I draw on Martin's book, BTM basically agreed to wait and see. 1949 was towards the end of the 1945 Labour government, and one of the actions of that government had been to create the National Research Development Corporation, NRDC. This was basically to generate economic regeneration in today's language, particularly in areas of science and technology. And as part of their remit, in December 1949, the UK government, through NRDC, called a meeting of companies that were interested in either punch cards or in electronics. And again, from the archives, it's clear that it took a while to set that meeting up. The companies didn't rush to attend the meeting. And this was, I think, almost certainly because they were not keen on cooperating on building jointly a computer. These were, some of the companies there were long-term competitors with each other. And here is the government suggesting that they should all get together jointly to build a computer. And so the meeting was not a success. So that was December 49. In December 50, the BTM board is still monitoring developments, and computers are coming up its list of priorities. In particular, things are starting to happen with Joe Lyons. Announcements are being made about the IBM 650. And so BTM decide that they need to find a partner who can help them build a computer to increase the computing power and flexibility of the punch card equipment that was going to remain the heart of their business. So they start looking round, and there were a number of potential partners. Manchester University, obviously, had demonstrated the baby in 1948, but they had links already with Ferranti. BTM had talked to Ferranti in 1949, prior to the NRDC meeting, and there had not been a meeting of minds. So that probably precluded Manchester. Cambridge were working with Joe Lyons. They'd agreed that Joe Lyons could basically copy the design of the EDSAC, but that machine was much too big, it was much too expensive for what BTM wanted to do. BTM are supplying punch card equipment to some very large companies, but also relatively small ones. So machines that were going to be in costing in six figures in 1950, 51 were unlikely to be the sort of product that the typical BTM customer was going to buy. They wanted something smaller and cheaper. The third option was NPL, and I sense that BTM didn't think a government laboratory was the sort of partner you want for a commercial venture. Pilot ACE was nearing completion, I guess, at that point, but I suspect it wasn't a good fit, and so that left just a few more projects around people building computers. There were obviously a few then secret or semi-secret defence projects, and those would not be appropriate as a commercial partner. And that left Andrew Booth at Birkbeck. I've taken, as you know, I've been looking quite hard and in some detail at the work of Andrew Booth. I think somebody actually said to me, and it may have been somebody in this room, they thought that metaphorically getting into bed with Andrew Booth was a high-risk activity. I think that's correct, because if you look at what Andrew Booth had actually achieved in early 1950, he had built SEC, it was complete at that point, but it had not been commissioned, and indeed, as you know, it never was commissioned. He went on to build APERC, he was already building a bigger machine. On the other hand, Andrew Booth, probably because he was always strapped for cash, could be bought for a relatively low price. In particular, Andrew Booth said well, in fact, he signed the agreement on the basis that BTM would supply punch card equipment. Well, BTM had metaphorically punch card equipment coming out of their ears. So that wasn't going to cost them a great deal, and a consultancy contract for Andrew Booth to give him their expertise. So although Andrew Booth may have been a risk, possibly arguably a high risk, he did come relatively cheaply, and also an agreement with him could have been terminated relatively easily, and okay, well, it wasn't a good idea afterwards, but in fact it turned out that, oddly, I suspect he was the best fit out of the options that were there. Improbable as it probably looked at the time. Here is a picture. Andrew Booth was a very keen photographer, but he clearly didn't like being photographed. It is extremely difficult to get good photographs of Andrew Booth at this sort of time in his life. This is a not terribly good copy out of Simon Lavington's book, but it's one of the few photographs of him face on. I do have another one of the first council meeting at the BCS with him again, but it also is not a very good picture. You will remember, if you heard my earlier lecture, he had a PhD in crystallography. He joined J.D. Bernal's department at Birkbeck in order to automate the calculations that were involved with X-ray crystallography. His father was a retired marine engineer, and he grew up in an environment where clearly people pottered about and made things out of metal. And so one of the things he was doing while he was doing his PhD towards the end of the war, and continued when he went to Birkbeck, was building all sorts of mechanical calculators and things a bit like specialised slide rules. And there are pictures of these. If you look at his 1948 book on Fourier transforms, you'll find there are some quite nice pictures in there of some of the things that he built. He then went on, you'll remember, to build the HEC-1 and then HEC-2, which were relay computers. And then in about 1948 into 49, he took the design for HEC-2, which was a von Neumann architecture. He took that and designed the simple electronic computer, SEC, which was an electronic implementation. Dickie Bird, who will enter this story very shortly, Dickie Bird was a student of Booth's and was BTM's prime contact with Andrew Booth. And Dickie Bird, who is himself a fine engineer, said, without any question, Andrew Booth was one of nature's natural engineers. He just, and it came to him, it just did it. But he combined that also with an excellent mathematical brain. He'd done a degree in mathematics as well. So he is a quite intellectually quite gifted individual. Here is the simple electronic computer from 1949. It's a picture I've used before. It shows this thing pointer. You'll see here. I'm sorry for those on this side of the. Oh, there we go. For those on this side of the room, you'll see the first real drum that Booth built here. The 21-bit wide drum that was provided the memory for this machine. It was finished in 1949 in terms of assembling it. Kitz's thesis, dissertation, an MSc dissertation, written in 1950 and published in 1951, says not yet fully working, and as far as I can see, looking at what's been written, it never was finished. Booth went straight on with the lessons learned and started building APEC. And this is together with Apex. These are the two machines for which Booth was probably best known. This machine was built at Fenny Compton, not Fenny Stratford. It was built at Fenny Compton. There was never any room at Birkbeck. Well, they could basically have at most two computers at Birkbeck. They had the HEC-2 and SEC in the small basement laboratory at Birkbeck. So APEC was built at home, and it was commissioned at Birkbeck in 1952 when SEC had been taken away. And after it was commissioned, it was delivered to the people who'd sponsored it, which was the British Rayon Research Association. And it used paper tape and 420 volts. And that's written up elsewhere. Now, the importance of this machine was that this was the machine that when BTM made their agreement to cooperate with Andrew Booth, this was the machine that Andrew Booth had just finished constructing at Fenny Compton and was in the process of commissioning in the famous barn on the wharf there. Dickie Bird, as we were told, went up there with two colleagues from BTM in March 1951, which was a very cold March. They went up to the barn on the wharf, and Dickie Bird and his two colleagues copied the circuits that Booth had created for APEC, and then took them back to Letchworth. And this machine, HEC-1, which, as you know, is now at TNMOC, that machine was then built at Letchworth. The date on which it first worked, we don't know. I think we can reasonably assume it was in early 1952. If it was anything before May 1952, it ran sooner than Booth was able to commission APERC. But on the other hand, Booth had himself, his wife, and one or two research assistants, whereas Dicky Bird had the whole resources of the BTM available to him. So that was HEC-1, and at some point in 1952 it was working, and the directors decided, probably, I'm not sure I've seen the exact date, but late 1952 I suspect, possibly early 1953, that they would start to sell this machine, and for that purpose they would demonstrate it at the Business Efficiency Exhibition in the summer of 1953. And so Dicky Bird was asked to build a replica, a copy of HEC-1. Delwyn will certainly can give you some more details. It's not literally a copy of APERC. They had learnt lessons, and there are differences between the two. But it's basically the same machine. BTM had a panel beater. Well, you're probably, I think, all old enough to remember when panel beaters used to do the bodywork for cars and things like that. Well, we have a description from Dicky Bird of the panel beater at Letchworth, who came along with a tape. It sounded to me rather like an undertaker, I'm afraid. He came along with a tape and said, oh, it's this wide, it's this high, yeah, okay, and disappeared off and produced the covers that you see here on this picture of HEC-2. A lot of the tabulators had individual features for particular customers. And so the panel beater was quite used to bodging things, and no doubt he had some standard components and so on. But that was the machine, and that went to the exhibition. Now, Kevin, when are we going to show the films? Do you want me to go through to the end of my presentation? Because some of the films are from, it's probably easiest if you do that, because otherwise we have to... I don't think it was been up. Yeah, okay. Here is the machine, the photograph of it playing noughts and crosses. In addition, Ronnie Michelson, who was the, in Dicky Bird's words, the first BTM salesman to understand computers. He was also a bridge enthusiast and an actuary by training, and he wrote a program that took 13 punch cards, each representing a different card from a pack of playing cards, and then used the standard ACOG conventions to tell the customer who'd selected the 13 cards what the correct opening bid was at bridge. There was a lot of interest generated in 1953 at the exhibition, and BTM then started to sell the machine. They christened the machine that was sold HEC-2M. It is said the M stands for marketable. It's not clear what else it might stand for. It's been suggested to me it might stand for maths, but I think that's probably not correct. So we'll take it that it's marketable, which is what Dicky says he thinks it is. So this is then the first production computer. They sold 7 of these, and very recently I've been trying to get a photograph. There are not very many photographs of the HEC-2M. There were only 7, and I knew where they'd been sold. People like Esso Refinery, they may have photographs in their archive. Trying to get in touch with organisations like that. It was tedious. And I know 2 of these machines went to Bedford, to ARA, and they're both aircraft-related research institutes, but and RAE, sorry, and anyway, good. And one of these has a website of enthusiasts, and they have no less than 40,000 negatives and images, which they have catalogued, which is the most extraordinary thing to have done. And I emailed them, and within an hour I had a reply saying they had searched their index and they had nothing on HEC-1 or BTM, but they did find a photograph of something called Hollerith. Was this anything to do with what I was interested in? I nearly bit the man's hand off. And so Barry Tomlinson, who is the man from Bedford who's been so helpful, supplied this photograph of the machine there, and it's one of the very few photographs we've so far managed to unearth, and it was used mainly for numerical work up there. 7 of those were sold, but they're quite small. The drum, which of course is the memory, the main memory of the machine, is really quite tiny. And so it became apparent fairly quickly that there needed to be a bigger drum and other changes made. And we move on then. The HEC-2M became known as the BTM 1200. And I've only found that very recently, reading some contemporary papers, marketing material. The HEC-2M was referred to latterly as the BTM 1200, and the 1201 was then a bigger machine which was large enough to do commercial data processing on it. And this is, I think, a marketing mock-up of the sometimes called a HEC-4 or 1201. And this machine then sold around the world about 80 1201s and the slightly larger 1202s. About 80, certainly I now have a list of 80, and I think there are a few more. So we're between 80 and 100 sold. Here's a picture. Morgan Crucible were the first people to take a 1201, and they produced quite a lot of these photographs. They also wrote a book, which Dickie Bird has given us a copy of, which was privately published, and is the most remarkable book. It describes the 1201 in great detail, and if you weren't aware of it, you would be utterly unaware that it was manufactured by BTM. You would think Morgan Crucible had built their own computer. Apart from a passing reference in the foreword, which says, we bought the machine from BTM, thereafter it is effectively it is the Morgan Crucible computer. But there is a picture from that book of the interior of one of the units. I don't want to take time because Delwyn will talk more about the hardware. The 1202 had a bigger drum. For reasons that are eluding me, I've got 4080 40-bit words on here. Somebody else said to me it's 4096. It probably is, but I got that 4080 from somewhere, and I'm not sure what the other 16 40-bit words are. But 4096 certainly sounds a more probable number. As I said, the total sales for the 1201 and 1202 together were around 100. It's an interesting machine because, as I said, BTM had these empire-wide rights. So India's first computer was a it was actually a HEC-2M. And it was also East Africa's first computer. I'll show a picture of that in a moment. I also thought I would introduce you to an odd use of a 1202. The Cambridge Language Research Unit is not, as far as I can ascertain, part of Cambridge University, but in the Computer Users Yearbook for 1963, September 63 edition, the Cambridge Language Research Unit says that the uses of the machine are machine translation, autocodes, development, I mean, there is a comma, but maybe it's autocodes, development, information retrieval, logical design, statistical analyses. Several years ago now, Dick Leatherdale and I both had copies of an interesting email from one of the field engineers who serviced this machine, who said that he went up there and fitted a horizontal adder as a special piece of hardware on that machine. That, amongst the interests of that group, that Cambridge Language Research Unit, was the translation of Russian into English. This, of course, is the height of the Cold War. It's a curious place for a 1201, 1202 to actually find a home. Wikipedia has no entry for the Cambridge Language Research Unit. It almost certainly is part of some group associated possibly with GCHQ or whatever. I'm just curious, it's just strange, it appears on the list. It's interesting, it does appear in the Computer Users Yearbook. If anybody has any information or can point me at somebody who might know something, Dick and I would...
And it's important. First of all, it was not part of the university.
Yes.
And secondly, what you need to work.
Okay.
Interesting. Yes.
Sorry.
What did he say?
Roger Needham, not part of the university, but David Harley was saying Roger Needham worked there during his student years.
During his PhD years.
During his PhD years. It would be interesting to know quite what they were up to. I think we can probably guess at least some of it. Here's the
Karen Spark Jones was there as well, I think.
Yes.
Karen Spark Jones. Yes, okay, so Roger Needham meets Karen Spark Jones at Cambridge. So around, warming their hands around an ICT 1202. Isn't that lovely? Okay.
Was that the very early demonstration there was a very early demonstration of Russian to English translation at one of these exhibitions or something, I think?
That could be.
Related to that?
It could well be. Booth, interestingly, translated quite a lot of computer science books from Russian, mainly on natural language translation, which he was interested in from the early 50s. He translated a number of books and so on into English, but I've no evidence of any connection between Booth and that group. The one demonstration he did that I'm aware of today was French into English. The 1202, I was sent by the same man who actually sent the information about the Cambridge Language Research Unit, sent this photograph of the East Africa Railways and Harbours Administration, 1202, in the early 1960s. And the reason for including it is partly, notice this is not an air-conditioned room. I'll read that piece of text in a minute. But it's not an air-conditioned room. You can see over here a coat hanging on it. I'm not sure whether it's part of the computer or not. But there's a coat hanging on there, there's a kind of conventional window there and so on, and it's been packed in. This is very much the world of punch card, tabulators and so on. It's not the swish world of large air-conditioned spaces. And I included it partly because this is the world into which BTM was selling. It was not, the world, the IBM glossy brochure world of huge expanses and so on. I'll read you this because it came with the picture. Because air conditioning as we know it today was unavailable in Nairobi at the time, a special extractor hood was manufactured to exhaust the hot air out of the CPU cabinets and direct out of the window. And you can see at the back here the extractor unit. So this really is kind of basic sort of technology. This machine took so much power that it could only be switched on in the morning after the local bakery had finished baking its bread overnight. And with that background, and that's 10 years later, one can see why the idea of building a copy of HEC would probably not appeal to BTM directors. That's a different world. The reality of their world were scruffy offices in hot country, well, partly, but it was a very different world from universities and research laboratories and so on. So very briefly then, what happened next? In late 1956, after the 1201 had taken shape, BTM started to devise a product range. They proposed having 5 machines, starting with the smallest, which would be an inventory computer, stock control and so on. P2, a scientific computer. P3, which became the ICT-1300, which we've talked about before. P4, which was an ICT-1400. I'll say a little bit about both of these machines on the next slide. The 1400 was a bigger version of the 1200, and in addition, it would have had, well, it did have magnetic tapes. And then the 1450 was the same as the 1400, but instead of having mag tapes, it was going to have a random access drum as backing store. But the 1400 still had a big drum as its main memory, so it was never going to be a fast machine. A 1400 was built. A prototype was built during 1958-59. BTM tried extremely hard to sell this machine. There's quite a lot of marketing material around, still around, which you find from time to time, about the 1400. Nobody wanted to buy it because fundamentally it was a first generation architecture. It was too slow. All sorts of better machines were available. So the decision was made that the project was going to be abandoned. And for about 2 years, the machine sat somewhere, I suspect with no activity going on at all. It was then transferred to Birkbeck College. I researched some years ago now, in 2006, I researched the history of the department of Birkbeck. The college annual reports are effusive beyond belief in 1961. The greatest beneficence ever in the college's history when ICT, quotes, donated the ICT 1400, a machine that would have cost £250,000 in the market, to Birkbeck College. Sadly, we know that in fact the company decided to abandon the machine 2 years earlier. And interestingly, Martin Campbell-Kelly's book, and Martin will have realised that quite a lot of this I've drawn from his book, and I'm grateful to him for that. But he records from the board papers, I assume, that it was sold to Andrew Booth for £5,000. Clearly, £5,000 changed hands. Whether, I find it difficult to think that in 1961 Andrew Booth was owed £5,000 in consultancy fees by ICT, as it then was. Maybe it was a kind of payoff which they didn't, it's a sort of quid pro quo for some reason. But To Birkbeck, it was a donation. Anyway, it really was not the kind of donation you wanted. 1962, most of you know, Andrew Booth had a bust-up with the college over not being awarded a chair, and so he went off to Canada with his wife. Birkbeck really wasn't prepared for this very big machine, the 1400. It had nowhere to put it. Once again, Birkbeck had no... So it went over the road. Those of you who know Violet Street, opposite Birkbeck College, is the School of Hygiene and Tropical Medicine. They obviously weren't using their basement because the machine was put in their basement. Unfortunately, the basement, possibly the whole building, didn't have a three-phase power supply. So the annual reports record that they sat around for a while waiting for a three-phase power supply to be installed. It also lacked device drivers. The machine had been abandoned before it was really ready for the market. So Birkbeck suddenly found that if it's going to make any use of this machine at all, they needed to write things like device drivers for magnetic tapes and so on. The academic staff at Birkbeck basically lacked the competence to do that, with the result that for about 5 years, the college annual report records in more and more depressing terms that there has been only limited progress. And in 1967, with the arrival of the CDC 6600, either its arrival or the announcement of its forthcoming arrival in the University of London, the machine is abandoned and it's recorded as being dismantled. Certainly there was a very big drum when I joined that department in 1970 as a research student. There was literally under a shelf in the corner of the department, there was a very big drum, which I had assumed had come from something like Booth's early machines. I now wonder whether it actually was the drum from 1400, but I don't know, I have no idea, but certainly we had this wonderful drum. I remember it had the most fabulous bearings. You could literally spin it with a finger and just run. Okay, enough of that. No, that's enough from me. Onwards, Delwyn.
Good afternoon, everyone.
Good afternoon.
So yeah, I'm going to talk a little bit about conservation of the HEC computer. Before I do that, I'm also going to talk a little bit about the technical aspects of HEC-1, something a little bit about the programming of the range, and then the differences between the different models that we've heard about, so HEC-1, HEC-2, and so on. So that's HEC-1. It's a serial machine, as you've probably gathered. It's based on 3 32-bit shift registers, and it has what we would call a 2-address instruction format. And that means an operand address and also a next instruction address for every instruction. So there's no concept of moving from one instruction to the next and decide where the next instruction is at every point. As Roger has mentioned, the drum is the only storage available on the machine, and that means that it's actually quite a slow machine. And it was, as we've heard, a very ingenious design. Andrew Booth was, by all accounts, a very good engineer, and he was able to create something that, if you compare the size of this machine with something like HEC, I mean, admittedly HEC is a much faster machine than this, but he was able to make a functional computer with so few components, and to have that working at such a cheap cost, and also with minimal power dissipated because you've got relatively few valves. So it's easy to understand why this was a perfect fit for BTM, who needed a machine that would work with their existing punch card customers who didn't have fancy premises. So actually what I should just mention as well is it's almost exactly 65 years ago now since Dr. Bird first went down to the freezing cold farm in Fenny Compton. So that was 1951, about March time. And Dr. Bird likes to tell a story about this. It was extremely cold, by all accounts. The bar had kind of rotten floors, and every time they put a chair down, one of the legs would go through the floor, so they had to be extremely careful what they were doing. And the only heating that they had available was a 2-bar electric fire. Now, apparently, Andrew Booth's father was quite careful with his money, and in order to save cost, he would go in every night and disconnect one of the 2 bars of this electric fire. And every morning, Dickie Bird and the team would reconnect it again, so they would freeze to death. So anyway, let's move on to the drum. So this is a photo of the drum off HEC-1 itself, and this is an original Booth drum. Now, later machines had BTM design drums, but on HEC-1 this is actually an original Andrew Booth drum. The little red circle you can see there actually says Wharf Engineering, and that's the company that Andrew Booth and his father formed in order to manufacture these drums, which they sold quite widely apparently, although I can't tell you exactly where into, but they did have a little business going there manufacturing these drums for a few years. Now the drum consists of 32 data tracks, and you can see arranged around the top you've got 8 head carrying pillars. Now, each of those carries 4 heads, and the heads are kind of interleaved in a cone in order to provide 32 evenly spaced tracks. And there's also a clock track, so you can see there's another little pillar at the bottom, and that holds the clock head, which is reading the serrations on, it's a kind of a serrated ring around the edge of the drum there, which forms the clock. So as I said, there's 1 head for each track, but these are actually switched using relays, so there's only 1 track can be active at any time, and you have a relay switching tree and a single preamplifier and right amplifier that's used to get the data in and out of the machine. It rotates at about 3,000 RPM, and that clock track actually provides the master timing for the whole machine. So again, this is an example of Andrew Booth's design skills, I suppose. Other machines at the time chose to synchronise their drums with the electronics, whereas this machine, you didn't need to do that. The whole thing was clocked off the drum, so if the drum, if the mains frequency varied, then the machine frequency varied a little bit. And it was, again, a very compact and economical design. So there's actually a small gap as well on the clock track, and that's needed in order to synchronise the machine with the clock track, otherwise you have difficulty telling where you are on the drum. And the overall clock rate was about 30 kilohertz, so very slow, even compared to its contemporaries. The 1s and 0s would be recorded on the drum using just the positive or negative magnetic flux, nothing fancy. No erasure was required, you could just overwrite previous bits. And also associated with that drum logic, there is what they call an input flip-flop, and that holds the digits that are read off the selected track of the drum. So onto the function table, front view on the right there, and you can see what it looks like at the back. So there's a 5-bit instruction field on HEC-1, and what the function table does is basically a network of resistors, and it decodes that 5-bit function into one of 32 lines, and you can see those coming out at the top there. And there's actually 10 lines coming in because the bit's coming in at a differential. Now those outputs at the top would have been connected originally to the order flip-flops throughout the machine. Now unfortunately they were all disconnected in the process of dismantling the HEC when it was removed from, presumably from Letchworth originally. And so, as we'll see later, there is some doubt over the veracity of the function table and the labels it contains, which is one of the mysteries that we've been looking into. So, next unit to talk about is the counter and coincidence unit. This is basically just a 9-bit counter, and what it does is it counts those 512 clock pulses that come off each drum track. And as I said, it also has a synchronization circuit that enables the machine to be counter to be synchronized to the drum. And the main job of this unit is to, when required, match up the desired word in its counter with what's coming around on the drum, and then to output a set of 32 pulses, which are then used in the rest of the machine to plot data to and from the drum. Now these are the pulses, very high power circuits, which is why they're encased in those metal boxes. Now Dr. Bird called these circuits torture for valves, He said, I wouldn't have designed them like this myself, but they work. And what they do, they have a transformer coupling between the anode of the valve and the grid, and that gives a tremendous kick when the input pulse comes in and results in very nice, strong pulses coming out. And again, it's a very compact design. Each one is one noise, and they're only one valve, a higher power valve than the rest of the machine uses. And those are two of the 32-bit shift registers that I mentioned. They're all very similar. The top one is the multiplier register, and the bottom one is the accumulator. So the accumulator, as you would guess, holds the result for arithmetic, and also it forms one of the operands for all the arithmetic instructions. Multiplier register, again, as you would guess, it holds the multiplier for the multiply instruction, and it also, in quite a clever design, holds the most significant, anyway, one half of the result. So the accumulator and the multiplier together hold the result that we get from the multiplier. So the arithmetic unit, this contains the Booth multiplier. So of course, this machine, one of its main claims to fame is it was actually the first machine to run that contained a Booth multiplier. So this is assuming that it did actually run before Andrew Booth's own paper design was commissioned. And that is where it lives. It's not even all of that unit, it's a very compact design. And the other main thing that this contains is a C6 counter, so-called. It's a 6-bit counter that's used as part of the shift instructions in the machine. So here's the adder unit, and I've shown the back of it to give you an idea of the kind of challenge we face with HEC-1 and not doing anything with it, basically. So, so the adder contains the add and subtract logic. It also contains an interesting mod. So you can see, I can find the pointer. You can see there, apologies to those on the other side of the room, you can see there's a sort of toggle switch here, double toggle switch, and various components which have been strung on the back of this unit. Now when we showed this Dr. Bird, he said that he didn't recognise any of this, which suggests it may have been a later mod to the machine. I will come back to it and explain what it's for, but this is one of the things, interesting things we've discovered as part of our documentation exercise. So control. Control is really the heart of the machine. It basically controls the rest of the units and fires the pulses around the place. One thing to notice about control, if you look at the previous pictures, it's a different construction, this unit. Now, in Dr. Bird's notebooks, he refers to what he calls a new control at one point. And so what we think happened, the machine originally, as we heard, was built as a copy of paper, and then later on the tabulator and card I/O functions were added by the team. So it's probably the case that when they tried to add these functions into the control, it was actually just easier to rebuild the whole thing than to try and modify it. So somewhat later on, they built a replacement for the control unit. And that's what we have here now. And you can see both on the front and the back that the construction is actually quite different. And again, Dr. Bird tells us that they have a lot of people coming around trying to sell them things at BTM. Occasionally they buy to say, okay, we'll take some. And this kind of scheme, this building scheme where you have all the components strung on the back of each valve on a kind of stalk with circular tag strips. This is one of those things that they got sold at some point in which they decided to make use of. Or possibly they got these as samples, who knows? But, okay, so the control panel of the machine, it's quite basic. You probably can't see the labels there, which is just as well, because quite a few of them are wrong. So the Dymo labels can't be original, because Dymo was only invented a few years after HEC-1 was built. And there are also paper labels, which are probably what the original labels were. But unfortunately, at some point, some of the Dymo has fallen off, and somebody has then helpfully reattached it very securely onto the machine, such that we can't really get it off now without potentially damaging the paintwork. So they will have to remain wrong, unfortunately. But it does provide a little confusion if you're trying to operate it. And this panel allows you to look at the contents of all three registers, and it also allows you to put in instructions manually and do things like start the machine running, and also single-step programs. So this is the tabulator interface, and this again is the new construction style, and this is really the main thing that the BTM team added to Andrew Booth's design. So this consists of circuits that are called CAN-controlled triggers, and these are used to debounce the very noisy signals that you get from the tabulator. And these are derived from contacts on a CAN in the tabulator. And so they need quite some debouncing if they're not to cause problems when they're introduced into the machine. It also contains drivers for the relays, again, to drive the outputs into the tabulator to print. And the connector at the bottom there is called a SHE connector, and that connector is where the tabulator itself would be connected up. So I'm sure you all know what punch cards are. There's one there to remind you in case you've forgotten. It's probably worth though just talking a little bit about tabulators and how they differ from what you may be familiar with if you're not familiar with this era of machines. So the first thing to say about the tabulators that were used with the HEC machines, all of them, they were all non-standard, so they were modified quite heavily from the standard models to work. And also this is one of the very first uses of punch cards on any computer. Although I think the IBM 701 shipped a little bit before HEC-1 went to market, certainly at the point that Dickie Bird and co were developing this, there were no machines on the market that used punch cards. So this was all breaking new ground, what they were doing at the time. So as you're probably aware, on later machines, cards would normally be read in from the left there, and you would have, on each column of the card, you would have some sort of character in ASCII or MSTIC form, and that would be an 80 column, an 80 line. Dick's going to contradict me. Anyway. Yes. Yes, so, but on the tabulator, the general way that they worked is that the cards were actually read in from the 9 row upwards. So in other words, the 9 and then the 8 row, the 7 row would be read in, and you would have 80 brushes across, which would sense all of the columns simultaneously. And the other thing to say is that normally at this point cards would have been alphanumeric only, and indeed most machines would only really do anything with digits. There was very little you could do with alpha characters on cards. And so for HEC-1, because they wanted to use cards to read in programs, they actually invented a binary format for that purpose, and that consisted of a single 32-bit binary number punched across one row of the card. And also on the same row you would have had the address on the drum where that was to be put. And so that enabled you to read in a program. There was also a card column known as the designator column, and that would be used to hold various control codes which would be used to tell it whether it was a binary or a decimal card, and also when to stop feeding and to return control back to the computer and start running the program we just loaded. So on HEC-1 in particular, only digits 0 to 9 could be read. There was no facility at all for bringing in text. And indeed, as far as I know, this carried on throughout the whole HEC range. It's interesting, Roger, you were mentioning that they were using a HEC machine for language processing. And that would have been fine on APERC, where you had paper tape and facilities to handle characters. But I wonder how they got the language in and out of the 1200, because the card I/O is decimal, essentially. They would probably have to have used binary.
Well, we use HEC-2.
Well, we'll come back to that. Yes. So just to note, of course, this means providing anything like a high-level language in the HEC machines would have been rather difficult, because you couldn't just punch a card up with a nice high-level text language and have it read it in. If anything, you would have to have punched a card in binary to do that. And it wouldn't have been easy because there was no character processing available on the machine really. And from that point of view, also just to draw some similarities with the Witch Harwell machine. Again, it was really designed for numerical calculation. There was not really any concession made to bringing in characters or thinking about doing general purpose symbolic manipulation. It was all about numbers really. Okay, so moving on to decimal to binary conversion. So this again is one of the major things which Dr. Bird and his team added to the APERC design. What we can see here is a diode matrix. Is that one of the only uses of modern diodes in the machine? In fact, most of the diodes are thermonic. So I'll try and explain the way this works. It is actually quite straightforward, but I'll see if I can explain it in a straightforward way. So one of the drum tracks is dedicated to holding up to 16 constants. And if you wanted to do decimal to binary, you would choose those constants to be 1, 10, 100, 1,000, and so on. But if you chose different constants, you could also do sterling currency conversion, or feet and inches, or anything that you can imagine that you can express in decimal digits. And so, of course, this was a very, especially sterling currency, was essential for BTM's customers. And again, the address of the drum track to be used for the constants was punched on the card itself. Now, as each card is fed in from the 9 row going upwards, so imagine you've got 16 columns with your numbers to be converted. As you feed in from the 9 row upwards, as soon as any of those columns contains a hole on the card, it sets a trigger that remains set for the whole time that the card is being read. And then as each, what they call index point is reached, so the index points are 9, 8, 7, 6, and so on the card. So as each one of those index points is reached, excuse me, a scan of that diode matrix would be initiated. And what that does is it allows the diode matrix to select one of these 16 column triggers in turn. And if the trigger happens to be set, it will cause the constant which is in that corresponding drum location to be added into the accumulator. And that happens for each index point. So you can imagine if you have a hole in 9, its constant will be added in 9 times. And if the hole is only in 1, its constant will only be added in once, and so on. And so this was a very elegant way of converting from decimal, or indeed any other units of measure into the binary that would be needed to process. So, just very briefly now on the order code. On the right there you've got, I don't know if you can read that, you've got the various fields of the instruction. 2 instruction addresses that I mentioned, operand and next instruction. You've got a 6-bit count field, which is used for some of the shift instructions. 5-bit function, and 3 spare bits. And I put under here, I put track delay with an exclamation mark. It must have been in there somewhere, and I'll come back to it later and explain what it does. So the instruction set is very simple, sort of early RISC instructions, I suppose, if you like. You can transfer to and from the drum, from the registers, including partial word. You could add and subtract from the drum into the accumulator, optionally clearing that first, which is effectively a move. You have left and right shift, you have the booth multiply algorithm, the multiply instruction, and you're able to test the most significant bit of the accumulator for positive and negative, based on that, effect a jump to either the operand or the instruction address in the test instruction. And for the I/O, you have an instruction that will feed a card, you have a print instruction, and a stop, which obviously just stops the computer at the end of the program. And interestingly now we have 2 other instructions here, TX to A and A to TX. Now these are written on the labels on the function table, but we have absolutely no idea what they do. And I think at this point we conclude that they probably don't do anything, but we're still not sure what they might have been intended to do. So answers on a postcard if you have any idea. Possibly the T might stand for teletype, if they might have thought at one point. Well, if that's true on HEC-1, that would be very interesting, because it isn't supposed to have that. Later machines do, you're right. Yeah, that is another option that I haven't thought of. I may have been intending to write that option.
I think Booth books.
Very interesting, thank you, Roger. That's very interesting. So we'll see if we might actually have that feature as a model of machine signal when we come to. One further thing to say on this. In order to optimize your program, it was essential to choose very carefully where you put the instructions. So the goal of that process called optimum programming would have been to minimize the total amount of time it takes to find either your next instruction or your operand for any instruction. And it sounds quite simple, but there are actually quite a complex set of rules that you have to follow for different instructions as to how many words you needed to wait before you could use the next word coming up on track. And also because as I mentioned earlier, there's relay switching going on, that actually takes 4 words to happen. So if you access the drum during that 4-word time, then you're likely either to get corrupt data or end up corrupting the drum itself if you were doing it right. And this is what the track delay bit is all about. So As you probably gathered, there's no addressing modes of any kind on the machine. If you want to do anything clever with addressing, you have to use self-modifying code. And that means that you wouldn't necessarily know when you wrote the program where the operand or less instruction is going to be. So in order to avoid this corruption issue, there was a bit added to the instructions only officially on HEC-2 going forwards called track delay. And what this did was it just inserted a 4-word delay between selecting the drum relays and carrying on and priming the counter and coincidence unit to start looking for that word. And so that would guarantee you wouldn't have any problems. Of course, it makes the program slower, so you would want to use that sparingly. And the other reason why you would need track delay is if you were single-stepping a program that runs on more than one drum track. As you imagine it, at the point you hit that single step switch, you've no idea where the drum is, so it's pot luck whether you end up getting correct data or something else. And so, for that reason, there's on HEC-2 and HEC-4, there is a switch on the control panel which permanently switches on your track delay, and you would use that when you're single stepping. Now, if you remember, there was a double toggle switch on the back of the adder unit on HEC-1, which shouldn't be there. It's not shown on any diagrams. And so what we discovered through reverse engineering what it does, this appears to be the track delay feature that was added on later machines. It's been retrofitted to HEC-1. Presumably at some point somebody just got fed up trying to debug a program and thought, right, that's it, we're putting this on. And it doesn't really logically belong on the adder either. Presumably there was just space on the adder available to fit the necessary components. And because, as I mentioned earlier, a lot of the wires have been disconnected, we know there's a couple of wires coming off from this mod, but we don't really know where they go. The assumption is they will be coming from one of the control register bits that isn't otherwise used, and there are 3 of those. And so far we can't be sure which one it was. But as we have no surviving HEC-1 programs, it probably doesn't matter. If we wanted to reconstruct that, we could attach it to any convenient bit. So, moving on then to the differences between the HEC models. So as we heard, HEC-1 there on the top left is based on the APERC machine, Booth's design. And if you like the APERC part of that design, you think from the notebooks that Dr. Bird kept, was essentially working by round about the end of 1951. If we're generous, maybe early 52. But unfortunately there was no eureka moment noted in the book, so we can't be sure. And the main thing that BTM did is they added that interface to the tabulator. In the case of HEC-1, it was an E6 tabulator, which at the time was, I believe, quite an elderly machine. And the reason why they used the E6 is because it was non-continuously rotating. And this means that the shaft in the tabulator could be told to pick up at any point. And that meant no waiting when you wanted to feed a card. You could immediately start the tabulator on its cycle and feed the card through. And probably towards the end of 1952, the decimal to binary conversion of all that tabulator logic was complete. Again, we can't be sure because there are no eureka moments written down. But certainly by the end of 52, the machine was running programs involving tabulation and conversion. So, HEC-2M, HEC-2, which is this machine here. As we heard, it's very similar, in fact, to HEC-1, but not identical. It was built primarily for the Business Efficiency Exhibition of 1953. And one of the main differences was the drum was the same capacity as HEC-1, but it was a BTM designed drum. So obviously they thought that they needed to bring this part of the design in-house. And we know that because there are surviving photographs from the Business Efficiency Exhibition showing that. It also, for some reason, it used a junior type tabulator instead of the E6. And that tabulator had a continuously revolving shaft, which meant that it was much slower to access cards and so on. And again, maybe someone more familiar with tabulators will comment afterwards, but it could be that BTM didn't want to show an elderly tabulator on their shiny exhibition stand, and so decreed that it should be an up-to-date model, even though that wasn't actually appropriate. Underneath it's still post office racks, same as HEC-1, it has nice panel Wheaton covers. The basic circuitry on HEC-2 has been standardised quite a lot, we understand, so just, not redesigned, but just turned up a little bit. And the other thing to note, just moving to this slide, so on the left there you'll see, well, either the front or the back of the machine. It's difficult to know which to call it, to be honest. Is that the front or is that the front? Anyway, the side where the valves are, most of the valves are on this side, but there is a blank panel on this end here. You can see that Dickie Bird is nonchalantly leaning against at the exhibition. Oh, by the way, he does tell a story that if he trod too heavily on that box at the end, he would short out all the power supplies in the machine and take down the stand, which they did at least once during the exhibition, presumably after this photo was taken. So on the right here, you can see the control panel M2 is here on the end, on the opposite side. So in other words, that's what's behind here. And I'll come back to that in a minute, because this is quite a controversial point. So after it was after BE had finished, it was taken back to Park Lane offices of BTM, and subsequently it was used for training and demonstration purposes, and also development of programming techniques. We basically have no surviving documentation on HEC-2. All of the information I've just given you has come from photographs and a few paragraphs in HEC-2 field engineering. So very little information. However, we do have a surviving program for it, and that is the Noughts and Crosses program, which, if you remember Roger's slide showing that board, that program was written especially for BEE by Dr. Bird. And one of my colleagues at the museum, Kevin Brunt, who I don't think he's here today, he managed to reverse, well, with the help of a flow diagram of the program, managed to reverse engineer the instruction format and some of the instruction codes for HEC-2 from those cards, from that card deck that was discovered. Sorry, it wasn't a card deck, it was a printout. It was a printout, tabulated printout of a card deck in a very obscure format. So it was quite a job of reverse engineering. And so from this we know that they completely redesigned the instruction set for HEC-2. The instruction codes bear no resemblance whatsoever to HEC-1 or HEC-2 or HEC-4. They're all different. Possibly revealing an engineering mindset rather than a software and programming mindset. Design process. Anyway. At this point, maybe, Kevin, you might want to introduce videos of this machine. That be the point.
The BBC were obviously at, no, I'm just shouting. The BBC were obviously at business efficiency at Olympia, and must have recorded quite a piece there. We have very short snatches of that, three short snatches. I'm sorry to show you all working out here. I'll see the OXO program first. Let's just get that as big as possible before I start it. I'll show you this twice actually, because it is quite a short piece, so it's worth seeing it twice. I apologise for the copyright. It is silent. Oh, it's fine.
So Dickie Bird told us at the HEC launch event that this program looked absolutely fine at the exhibition until a party of children came along and pressed all the buttons at once. That bugged it.
There we go. I think it probably is. I'll show it again, but I was obscuring the screen.
I believe that's Ronnie Michaelson, isn't it?
That's Ronnie Michaelson doing the demonstration, yeah. Which is, I think, as you said, Dickie described as the only salesman that actually appreciated what he used.
Playing games. I think that the actual board itself was wired in some way so the machine thought it was reading a card. see there how they are being read in downwards as well as recess.
We have started the search for the originals of all of these as well. And the final one is actually the drum as well. Actually, some shots of the front of the machine.
Okay, so this shows you the drum. You can see it's similar, but it's not the same as the HEC-1 drums that we got at the booth drum. You'll notice the layout is extremely similar, but again, not identical to HEC-1.
I think we suspect that that's possibly the first time a computer was shown to the general public on an exhibition like that.
Right, only another 3 hours to go, and then we can go to the trial. So, right, so HEC-2M and HEC-4. So, this is actually a slide of chassis from the 1202, but the same type was used on HEC-2M as well. HEC-2M, of course, the first production machine. It was, before it was known as the 1200 that Roger mentioned, it was also known as a Type 560 for style and documentation. And it was constructed using these pluggable modules which could hold up to 18 valves. This one obviously contains 10, but you can see there's plug-in some cutouts for another 8 that could be fitted. Now, apparently, when Andrew Booth heard about this scheme to change the construction method, he was initially very sceptical. He was very much a connected direct kind of engineer, didn't really approve of connectors, and basically prophesied that the machines would be unreliable because of all these extra connectors. Well, as far as we know, they actually were very reliable, so on one occasion he was wrong. Obviously, there's great benefits to this construction. It means that individual units can be easily pulled out and exchanged in the field. Also, when it's installed in the machine, all of the valves point into the centre of the machine, which makes it easy to pull them, and it also gives handy access to all of the components and which you need as an engineer to maintain the thing, get the slope probes on and so on. So, quite a clever construction technique and first used on HEC-2M. Now, one of the major improvements that was made on HEC-2M was the ability to read in up to 12 binary numbers from one card. So HEC-1, you do one card per instruction in your program. Obviously that was very slow, but program loading very much speeded up. And also they went back to a non-continuous type of tabulator. Now I'm not actually sure what the model used was, but it's we understand it's non-continuous again, like HEC-1, which again improves those speeds of reading cards. The drum size was doubled on HEC-2M to 64 tracks. Also, it wasn't actually installed in the main machine. It was, sorry, that's ignore that. It has an optional stop bit in the instruction format, which again is a debugging aid. It was an early hardware breakpoint, if you like. It's a control panel switch that enables you to select the machine will stop on any instruction that has the optional stop bit set. And it also is the first documented use of this track delay feature that I mentioned before. So HEC-4, lots of additions on HEC-4. As we heard, it was marketed as initially Type 1201. This still had the 1024 word drum that was used on HEC-2M, but at some point quite soon after that, the 1202 was introduced, and that quadrupled the drum size up to 4096. It does occur to me, Roger, the discrepancy of the 16 words, maybe because one drum track was reserved for output instructions, and so possibly a 4080 is usable for programming. One of the other enhancements was the use of electronic switching instead of relay switching, and that was between adjacent pairs of tracks. So you still have the relay tree, but if you were moving between adjacent tracks on the drum, 0, 1, 2 and 3 and so on, that could be done immediately and avoided that forward access time penalty. The word size was increased to 40 bits from 32, and that that meant also increasing the count up to 7 bits to cope with that. And also 2 entirely new registers were added, Q and B. And these would be used, could be used on arithmetic operations instead of using the drum. So on HEC-1 and HEC-2, every arithmetic instruction involved a drum access, whereas on HEC-4, if you're using Q and B, you could avoid that extra drum access. And this made a large difference in the speed of multiplication in particular, because the multiply instruction involved accessing the drum each time round the loop for the multiple repeated adds. There was also a hardware divide instruction added, admittedly with some restrictions. The answer had to be less than 1, and both numbers had to be positive. And if you couldn't guarantee that, you had to use a software routine, which is helpfully published in the programming manual. And there were many enhancements made to the decimal to binary conversion, so you could use all four registers, for instance, and the conversion track was pluggable to a certain extent. And finally, they added the reverse conversion for printout as well, so binary to decimal, or indeed Sterling, anything else you wanted, depending on the constant you choose. And that would obviously be for printout. There were new instructions for block addition, so the ability to add a whole set of words from the drum into the accumulator, which I know it's actually not the same as you've mentioned, Roger, but it's a similar instruction. And also group accumulation, which enabled you to add your successive drum words in turn into the 4 registers. Enhancements in testing as well, you could test any bit in a word, not just the top. And there was also ability to test for any ones in either the topmost or bottommost end bits of the word. The accumulator. And finally, printing and punching instructions happening in the background. And that involved the use of this dedicated drum track to store what you were about to output. And that could be accessed independently of the rest of the computer operating on the rest of the drum. And obviously had its own amplifier chain and so on. And of course that's a kind of early example of DMA, if you like, or autonomous I/O. So, moving on now to the documentation process that we've been undertaking. So, since October last year, myself and a small team have been engaged on basically sketching out all the circuits and trying to understand the machine, how it fits together, things like that. Now, we don't have very much information to go on when we started. This is one of the main documents, or an extract from it anyway. You see it's kind of a block diagram format, and that gives you an idea certainly of what the machine's supposed to do. Contains quite a lot of notation which is not really defined and in some cases not really clear what it means. And there are quite a lot of inconsistencies on the diagram as well, so there are numbers used everywhere to refer to as signals, but they don't all match up. And some of them are used twice and things like that. So that was one of our major helps. The other thing we had access to was the thesis of Norman Kitts that Roger mentioned earlier. This was on the SEC computer that Booth designed. And it gives an idea of the kind of circuits that Booth would have used and therefore what we would expect to see in HEC-1 as well. We had a HEC-2 field engineering manual. Again, we didn't know really at the outset how similar those circuits would prove to be to HEC-1, but it was a useful guide as it gave an idea of the thinking and the terminology and various, especially to do with the tabulator interface. It's quite a lot of arcane terminology, which if you're not familiar with that technology is difficult to get your head around. And finally we had various information on HEC-4, so a programming manual, and even a set of partial schematic drawings for HEC-4. So what were we actually hoping to learn from this process? Well, primarily, and most significantly, is the machine we have actually HEC-1 or not? It might seem a surprising question to ask, but actually when the machine came from Birmingham, it had a notice on the front that identified it as being Apex by Booth. Well, we knew that wasn't true because there were photos of Apex. But it did cast some doubt on, is this machine, we believe it's HEC-1, but is it actually? We have a drawing and we have a machine, but there's nothing on it that says HEC-1. So that was obviously one of the goals, to prove that. Secondly, we wanted to show how close the machine was, in fact, to the original schematic that you can see here, had it been modified in any way. And thirdly, that original Booth drum, very rare. We wanted the opportunity to study that and maybe learn a little more about how that works. So this is kind of the output. I don't know if you can't read that, it's just to illustrate the kind of diagrams we're producing, but this is really the output of our process. This is a modern CAD drawing, electronic CAD, and it's really the final stage in our documentation exercise. The way that we approached this, as you saw from the diagram of the adder, and believe me, the whole machine is like that and works. There are wires everywhere, everything is disconnected, there are lots of paper labels, most of which are illegible or have fallen off. And when you can read them, we don't really know when they refer to sort of 3M or something, we don't really know what that means. So some of it we have worked out, but it was very far from being plug and play, shall we say. So the way that we approached it was chassis by chassis, go through on paper each valve, sketch out the circuit coming from that valve to its nearest connection points, be that a valve or a tag strip or a connector, whatever. And most importantly, assign unique identifiers to everything. So every tag strip, every valve base, every chassis connector, every cable, every pin on every connector, you need to have a code to refer to it. So later on, when you've forgotten the exact detail of what you're doing, you don't get hopelessly confused. So this we've managed to do, and we've tried to stick where possible to the naming conventions that we've worked out from the original labelling. And of course, one of the problems with that process is when you draw it out on paper like that, it really makes no sense. You just end up with a load of score and no idea whether it's correct or not. And then the process of CAD, turning it into these kind of drawings, moving things around, circuits start to slowly take form, and then once you've worked out what input or output might be, you can then get a handle on what this might be doing and then trace it through. So actually, although when we started out, I have to say I particularly feared it might be a terrible drag doing this documentation, but it actually has turned out to be quite intellectually interesting process to do. And I think when we have the full results, it's going to definitely be worth it, because this machine will be very well documented at the end. And where we are now, we've traced everything onto paper, and some of the chassis are still left to be drawn up into CAD. And no doubt there will be some going back and correcting mistakes as things take shape. So what have we learned? Well, so this is the controversial picture here. Luckily, Dr. Bird is not in the audience. In order to put this machine back together, that is the only orientation which will work. The cables that come off the right-hand side of that control panel are so short that they could not possibly reach any other way, and they go directly into the left-hand side of the chassis next to them. And actually, if you think about it, this makes perfect sense, because this is a prototype, it's not a production machine. The engineers working on it, so they really don't need to see the valves at the front. What they want to see is the connections at the back where they put their oscilloscopes on. See what's happening, and they also want to be able to move the controls at the same time. So it makes perfect sense to have done it that way. And if you remember back to that picture of HEC-2 that I showed you and drew your attention to, you'll see that actually the relative positioning of the circuitry is pretty much the same. And the control panel on the HEC-2 is indeed on the other side of that end chassis. Unfortunately, this does run contrary to Dr. Bird's memory of how the machine was. I've tried to persuade him, and I'll continue trying, but at the moment, it's a draw, I think, on that. So, yes, so we've learned that the circuits are in fact very similar to HEC-2M, so they obviously made most of the changes to the basic circuits going from from Labour into HEC-1, so things are quite straightforward. We've been able to discover the functions of all the chassis, and I went through those with you earlier. So quite a few of those chassis are not labelled. It wasn't immediately obvious when we got the machine what they did. And of course we've discovered this unexpected mod so far, and there may well be others as we go through and complete the other units in CAD. It's a track-delay feature, and there could be potentially others. In particular, we are looking out to see if those stray instructions might actually do anything. At the moment, that isn't clear. So our future plans for the machine. Sorry, that's not that. Yes, one of the things that actually you touched on earlier, Roger, when we got the machine, we found that although it was mostly populated with valves, as you can see there, actually they were in random positions. So the valves consist of a mixture of double triodes and diodes for the most part, but they've just been stuffed in any which way. So obviously at some point they've all been removed for transit, and maybe someone didn't realise there were two different types, and then they just put them all back, and it doesn't matter. But interestingly, when we started trying to put them back in the correct positions, we found we had rather a surfeit of diodes and not enough triodes left. So it raises the question as to whether any of the valves in the machine are actually original, and how much of it got borrowed when it was at Letchworth or at some previous stage in its life. And certainly a lot of the cabling has also been borrowed at some point. There should be lots and lots of coax cables everywhere carrying clock signals, and almost all of them are missing. So at the moment our mandate for this machine from Birmingham is to do conservation and documentation work, and that's hopefully going to be completed in another couple of months' time. But we have also been considering possibilities of a restoration. Now, having gone through this process, we have really, initially what looked like a hopeless case is now looking a little bit more workable, potentially. I'm quite confident at this point that when we complete our documentation, we will have enough information to enable the whole thing to be reassembled, and all of those thousands of loose wires and hanging off components will know definitely where they go. And our experience from running Which, or Harwood machine, for the last 4 years has really taught us that the majority of the components that are used in HEC-1 are likely to be still reliable, or at least tolerably reliable. Things that we know are unreliable in Which, luckily there aren't very many of them, or there are none at all in HEC-1. So things like wire wound resistors, which causes a lot of trouble on the Which, trigger tubes, there's nothing like that. And I think, with restoration, there's always an argument to be made both for and against restoring any machine. The argument against is always, well, any restoration involves changing the original artefact, it's a historical object, how much intervention should be done. Against that, I think the argument, particularly for this machine, because it is in quite a fragile condition, there's an awful lot of broken joints, components hanging off, and so on. At the moment, we are in a very good position to really put it back together in the way that it was originally, and leave it in a much better state for the future. If it goes too much further, it might become very much more difficult or impossible for anyone to do that. And actually getting the machine working, of course, forces you to find all of the broken joints and replace all of the cables, and guarantees that everything is correct and that your documentation is correct. Not to say, of course, there would not be challenges, quite significant ones. Power supplies, always a challenge in any machine. But in this case, they're actually quite simple, so I'm not too worried about that. We could quite easily build a modern replica power supply and hide it where it wouldn't really be noticeable. The drum itself is quite fragile, and it's also unfortunately damaged. Some of the oxide coating has already been scraped at some point in the past. So we're not really planning to do anything with the drum other than possibly attempt to read its original contents, but certainly we wouldn't want to risk it running it on a machine or on a restored machine. So initially we would seek to emulate the drum. You need that anyway because the whole clock comes off the drum, so to do anything with any of the circuits we need a clock and a reliable clock, so that would be the first thing to do. And then it would be quite interesting to try and build a replica of that drum using modern components built in the same fashion. So that's definitely something that we'll be looking into. Of course, there's no tabulator, and the chances of getting an original tabulator are zero because it was modified especially for the job. So given that it appears not to have survived, I think that isn't really an option. But actually, in a museum environment, a tabulator, even if we had it, it's not ideal. It's mechanical, so it requires a lot of maintenance, and it also needs consumables, which everything like punch cards and ink ribbons and even fanfold paper and like real paper are getting difficult and expensive to get hold of. So even if we had the tabulator, we probably wouldn't use it very much. We would certainly want to emulate basic tabulator interface so you can load programs into the machine somehow, rather than typing them in instruction by instruction. And the other thing that we would probably seek to do is to build, maybe not at that scale, but some kind of replica of the Oxford board. As we mentioned, we have the original program for HEC-2. It wouldn't be too difficult to change that program so that it runs on HEC-1. And that, of course, gives the visitors a very nice interaction with the machine, which is, visitors generally are not that technical and they don't probably appreciate the details of the booth multiplier as this audience may, but so this is an important consideration. And finally, with possibly some historical caveats, we could consider a teletype interface to the machine. Again, Apex have this, or Apex have this interface. It would be very easy to add because of the way the machine is constructed. Although the HEC machines never had them, it would at least, given its pedigree, it would have some historical justification. So basically, watch this space, and we will be putting together some kind of plan and go to Birmingham to propose something at some point in the next few months. Thank you very much.
Thank you very much indeed, Delwyn, Kevin and Roger. Does anybody have any questions or comments? And there is a microphone which we should use. Dick.
When I moved to British House South next to Putney Ridge about 40 years ago almost.
Is it switched on? There's a light.
Boom.
I was saying that I moved to British House South next to Putney Bridge about 40 years ago. I was told that the reason it was sited where it was is because there was once a proposal to build a very large valve computer, and the adjacency of the river would have been useful for cooling purposes. I'm not sure whether that's true, but it seems to me to be reasonable that that large valve computer might well have been the 1400s. And that the enduring legacy of the 1400 was nearly half a century of Putney, of the presence of ICT and ICR. Richard Dean might know more about that than I do, as indeed might happen.
I think this is a bit of folklore. I moved to British House South in '61, and there's no evidence of cooling because I was involved in installing computers and air conditioning plant and all the rest of it. The interesting thing about these computers is that they were built to go into punch card installations where there were, as Roger has quite rightly said, very little provision for air conditioning or raised flooring. Computers came along, and that was one of the big things we had to change in British House South. There's some other comments I'd make, but perhaps let other people speak before we can perhaps come back to me later. Just head off that bit of folklore.
I'm Richard Dean. I joined British Tab in 1956. And after basic training, I went up to Birmingham as a technical serviceman in one of the districts. And I'm not quite sure when, but it must have been about 1960, 1 year. Either way, I was selected as the first person to go on a 1201 course, which was held at Bradnam Manor, a rather attractive National Trust property about 10 miles north of High Wycombe. And it was a 3-week course. We were divided into 3 syndicates of 4 each. At the middle of the week, there was a single machine stuck in what had once been the horse stable, I think, at the back. And we were supposed to write and test a program in that 1 week, using only machine code, as there was no assembler available at that point in time. And it was a delightful late summer period of time, and there was a very nice lawn on which you could play croquet or bowls, and my syndicate and another syndicate found the programming a bit difficult, not making much progress, so we very kindly gave up all our time to the third syndicate, which spent all its time trying to get its program to work, and they didn't get their program to work either. Almost 3 times as much testing time. Fortunately, I never had to program a 1201. I only got involved in selling a 1201 very late in its life, when I was working down in London, and 1202s were being remaindered at a very cheap price, and I was involved, not actually as a salesman, but doing some sales support on selling that. And the final connection I have is that if Morgan Crucible were about the first commercial user of a 1201, I worked to get them to agree to replace their machine and help set up the programming teams that programmed the next machine, which I think was a 1903, but I wouldn't absolutely guarantee that.
I'll confirm it was a 1903.
So that's my involvement with 1209.
Thank you very much.
Thank you, Dan. Two comments. First of all, let's continue the Morgan story. The 1200 was a very reliable piece of kit. For two reasons. Raise the question of why did they choose the slower tabulator for reliability. It may have been slower, but it had a really heavy duty clutch, and the other one was faster, but it broke a lot quicker and it was a lot harder to mend in a real situation. Extending the story of 1201 at Morgan's, it was nice to see pictures of that particular machine because that was the engineer machine that I first met as a 1201. It's nice to know that when I first met it, just in the early 60s, that it was there all the way through to the 1900s. The only problem with it, with anybody who's worked on valve equipment bites if you don't respect high voltages. And Morganite carbon, there's a clue in the name. They machined graphite, which made dust, which made for some very, very interesting fault finding. But basically on the tabulator front, reliability.
Oh dear, you've got me running about this house. Anyway.
It's a small point, this, not an engineering point, but a marketing point. Interesting to hear the mention that at one stage a type number 560 was being considered. But this implied that this machine was a continuation of the existing calculator family, 540, 542, 550, 555. And somewhere in the upper regions of ICT house, they must have decided, no, this is special, this is different, it's bigger, it's better, it's newer. It's computer, it's got to have a new class of number. So jump straight into the thousands.
Yeah, that number comes from the HEC-1 field engineering manual. So at that point, certainly they were branded HEC-1 primarily, but underneath the middle piece it said type 560. Later on, as we know, it was referred to as the 1200, presumably after that transition. And interestingly, in the HEC, we have a very early copy of the HEC-4 program, 1201 programming manual that came from Dickie Bernard, and it has hand corrections on it. And in a couple of places, it actually says type 561 for 1201, which has been crossed out.
Oh.
So they must have made that decision at some point during HEC-4 development that it would be called 1201.
Just a comment. Somewhere kicking around, we've got some 1201 pre-printed programming cards.
Which will make sure you got to follow.
And the other one, really a follow-on, where did they get the number 1200 from? Follow up by the 1300s, 1400s. Any idea where the number came from?
Just to explain a bit of and tie in with what Hamish has said, I think this presentation has been very much about the computer developments in BTM. In parallel, BTM had an ongoing series of developments for doing it the other way around, of attaching computing capacity to tabulators. This HEC was developing a computer and attaching a tabulator. There's a series of developments that went on that have been referred to as 541, Hamish has referred to them, 541. 550, 555, which were being sold and no doubt demonstrated at the same business efficiency exhibitions, but were less capacity and more doing classic card applications of read a card, do a little bit of calculation, and punch another card. So the company had that stream of development on the go, and the two teams that were doing these developments were working in the same physical area, and the write-ups indicate that there was a fair bit of sort of speaking to each other and cross-talking. But another thing to position it is very much, these were sort of backroom developments within the company, down at Letchworth. The marketing and sales people were in London, and it was a sales-driven company, very much to do with maintaining its rental revenue from the existing customers. It had a product planning, or a planning outfit, which is referred to very scathingly by the engineers. And that product planning outfit, or it was very much a business and financial planning. They're more concerned with the revenue streams from existing products and when to introduce new products. But that's product planning people, they would be responsible for any of these names. I think the 560 reference is probably just either a marketing, some transitional thing just to reassure customers or something, but there were definitely two streams of development.
I wanted to add a little bit to the mysteries of the Cambridge Language Research Unit, which Roger mentioned. In 1963, I was working at Farnborough at the Royal Aircraft Establishment. I was put in touch, my mathematics tutor had been Richard Goodman, who'd worked with Booth, I believe, and suddenly had bits of Booth kit in his lecture room in Brighton. When I was at Farnborough, Richard put me in touch with a man called Gordon Pask, who ran an eccentric research outfit in Richmond. When I joined Gordon in 1964, the other research associate, there were only two of us, was an American called Richard Feldman. And Richard used to vanish on, I think, a Tuesday evening, and he had a very tame dodecahedron. He used to leave his dodecahedron in the left luggage office at Richmond Station. He then went to the Cambridge Language Research Unit and slept there for 2 or 3 days a week, developing some very early cellular automata simulation models. This was well before the economy game of life stuff. So Gordon was working on this, and the connection there was that one of the directors of system research, Gordon's company, was a man called Bobby McKinnon Wood, who worked closely with Margaret Masterman, who headed the Cambridge Language Research Unit. And I think there was an intelligence connection there, because my work at system research was connected with modelling in intelligence systems, in my case particularly connected with crime intelligence. And we're developing that, models for that, on an ICT, they call it, was it 1301 in Brighton? I think it was 1301, because they came in with me several times to Brighton to develop these models. So there were intelligence connections. Cambridge Language Research Unit, very, very interesting organisation. Maggie Bowden at Sussex University also did some work there. So just happy to do this. Thank you.
Simon, did you want to?
Oh, yes, a brief one. Kevin. Kevin said that he thought that the business efficiency exhibition in '53 was the first time a computer had been. Yeah, I can't exactly remember the time, but it's worth looking at the HEC-1, which I think was exhibited in April '53 at the Physical Society's annual exhibition.
Right. Good.
Well, thank you very much for your comments, contributions and questions, and thank you again, Delwyn, Kevin and Roger. Now, our next event is going to be on Wednesday the 11th of May here at 2 o'clock for 2:30. Coffee will be served from 2 o'clock.